Welcome to POWTECH Virtual Talks on Rare Earth Elements and Energy Revolution, Characterization and Processing. Mr. Duan from Netzsch will talk about improving magnetic properties of rare earth magnets by fine grinding. Have fun and enjoy.
Okay, so if we are ready, then I will start. Hello to everyone. My name is Zhenyu Duan. I'm from company Netzsch. Today, I would like to discuss with you about the topic of processing rare earth magnetic material by fine grinding technology. First, a short introduction of Netzsch. We are a German group which has 3 business units, including thermal analyzing, grinding and dispersing, and pumps. We are the worldwide technology leader in all the 3 business fields. I'm coming from the business unit grinding and dispersing. So from this business unit, we provide wet and dry grinding, wet mixing, dry classifying, and also other material processing technologies to our customers in different industries. The main focus of discussion for today is about rare earths. You must have heard the word rare earths more and more in the last few years from different channels. But why discussions about rare earths are heating up? As the first speaker, I want to discuss with you a little bit about the background here. First, let's have a review. What are the rare earth elements? So if we look into the periodic table, there are 17 elements which belong to the group of rare earth elements. There are 17 nearly indistinguishable soft heavy metals. They tend to occur in the same ore deposit and show similar chemical properties, but with very different electronic and magnetic properties. We call these 17 elements rare earths. So what are rare earth elements used for? Here's an overview of possible application of rare earth elements. So due to their very unique properties, they become necessary components for hundreds of products across a wide range of applications, especially in the high-tech products. So they make possible the high-tech world we live in today. Everything from the electronics to the enabling of green energy and medical technologies to supporting a lot of essential telecommunications and also defense systems. Although the amount of rare earth elements used in a single product may not be a significant part of that product by the weight, value, or volume, but the rare earth elements can be necessary for the device to function. Today, actually, over 20% of the rare earth elements are used for producing magnets, which will be the main focus of my presentation. Because of the important application of rare earth elements, they are called the seeds of technology or technology metals. They have been listed in the category of strategic elements in many countries. Therefore, exploitation, acquisition, and application of rare earth elements are closely linked to the economic and political competition between countries like US, China, and also Europe. At the moment, China reserves more than 35% of the worldwide rare earth materials. While talking about the producing of rare earth elements, the US was the world's leading producer of rare earth elements from the 1960s to the 1980s. However, today, China has become the dominant producers since the 1990s. Several powder processing technologies are involved in the producing of rare earth elements themselves and also the downstream products which contain rare earth elements. So it makes great sense for us who are in the powder industry to discuss about the processing of rare earth elements. So just now we mentioned magnet is one of the most important applications of rare earth elements. So in the next slides, we will have an overview of the rare earth magnets and also the current fine grinding solution which is used to produce rare earth magnet, especially the type NdFeB magnet. Actually, we do have a lot of different types of magnets. In general, they can be divided into soft magnet and hard magnet. Hard magnet is also named permanent magnet. A permanent magnet is an object made from a material which is magnetized and creates its own persistent magnetic field. Permanent magnets made from alloys of rare earth elements are the strongest type of permanent magnets. There are two main types of rare earth magnets. The first one is NdFeB magnet, and the second one is samarium cobalt magnet. They produce significantly stronger magnetic fields than all the other types of permanent magnets, such as ferrite or anickel magnets. A sintered NdFeB magnet is the most widely used type of rare earth magnet. It is a permanent magnet made from alloy of neodymium, iron, and boron. Developed in the 1980s, it is the strongest type of permanent magnet available commercially today. So it will be our example product for discussing the fine grinding solutions. Here is the typical process of producing the sintered NdFeB magnets. The production follows the typical powder metallurgy route. So during this process, the alloy after melting has to be changed to a form of powder. Several different steps are involved here, including the strip casting, hydrogen decryptation, and jet milling. Jet milling is the final key step, which produces the fine powders that have a particle size normally in the range of 4 to 5 micrometers in average, to ensure the good properties of the final magnets. The traditional jet mills used in this application is the so-called fluidized bed jet mill. As you can see, the bottom part of the mill is the area where the grinding effect will happen. So the grinding gas will come through several grinding nozzles in this grinding area, and they will accelerate the particles inside the grinding chamber to impact with each other. By this kind of impact force, the effect of reducing the particle size is generated. Afterwards, the particles will be transferred to the top part of the mill. In this area, a rotating classifier wheel will select particles which have different particle sizes. The result will be only the fine particles which have achieved our target size can pass the classifier wheel and leave the mill. The coarse particles will be rejected by the classifier wheel and stay inside the mill for further grinding. In this type of mill, it's extremely important that a constant amount of materials stay inside the grinding area during the complete grinding process. Only under this condition, the mill can achieve the best grinding efficiency and a constant final particle size distribution. Due to this feature, that constant material has to be kept during grinding in the mill, the fluidized bed jet mill creates different difficulties and disadvantages for processing the sintered NdFeB. First, because at the starting phase and stopping phase of the mill, the material amount inside the grinding chamber is always changing. The direct consequence from this is the final particle size distribution of the milled products during these periods are not constant. which means you have variations of particle size distribution with your final products. Besides the particle size, variation also exists with the composition of alloy during those periods. So normally you cannot use the powder during these periods as your final qualified products. Next point is after milling, you always have certain amount of materials stay inside the grinding chamber. Those materials typically contain coarse particles and also possible hard to grind materials. So how we can remove those materials out of the mill to restart a new production? We cannot just open the mill chamber and take out the materials directly because the material is highly active to the oxygen in the ambient. A typical way is to open the nozzles in the bottom part of the mill body and to reduce the speed of the classifier wheel. In this case, the gas coming from the bottom nozzle will help to transfer the materials to leave the mill through the classifier wheel. And then they will be collected as the outlet of the following system components like cyclone or filter. But the point is, during this process, part of those materials, they will always stay inside the complete system. It means you have to take care or to cleanse those materials before the starting of a new production. Otherwise, they will be the possible contamination source for your new products. If you have worked with such a fluidized jet mill for sintered NdFeB, then I'm sure you have met above problems or difficulties. That's why we as Netzsch will bring you a new jet milling solution for your sintered NdFeB magnet production, which could solve the former difficulties and provide you additional benefits. This is our new jet mill, which is called MJet. At first glance, it already looks very special, right? Actually, this is a very special designed jet mill. It's a spiral jet mill with integrated classifier wheel. This is our unique design, and it's specially designed for processing the rare earth elements. Here you can see the basic structure of this mill. The light green part is the grinding chamber. So surrounding this grinding chamber, there are 6 grinding nozzles marked in blue. The grinding gas will come through these grinding nozzles and will accelerate the particles in the grinding chamber to have a spiral movement inside the grinding chamber. During this movement, the particles will impact with each other, and the purpose of reducing the particle size will be achieved. Afterwards, the classifier wheel marked in red will control the final particle size. With our MJet, we will bring you following benefits. First, the MJet can help you to get final products. So why do we need final products than before? We know that there's a trend to further optimize the NdFeB magnets by reducing or eliminating the heavy rare earth additions. So one possible way to achieve this is to further reduce the particle size of the NdFeB magnetic material. So now this becomes possible with our MJet without giving up a satisfied throughput rate. So with the MJet, you have the chance to produce a final product of which the D50 value can be in the range of 1 to 3 micron. The second benefit is our MJet will produce much less content of superfine particles below 1 micron when reaching the same D50 value as the other type of jet mill. Plus, the wheel-controlled coarse particles Finally, our MJet is able to provide you a narrower particle size distribution, which could also help to improve the final properties of your magnet. And just now we discussed that many difficulties in the traditional fluidized jet mill is coming from the point that constant material has to be kept inside the grinding chamber during the grinding process. Now with our MJet, you don't need to take care about this point anymore, because the grinding effect with our MJet is now independent from the material amount inside the grinding chamber. That also means you will not have the variations of particle size distribution during starting and stopping phase of the mill. Additionally, after grinding, there will be no product residue inside the grinding chamber. Another point, if there's any hard to grind particles, for example, alpha iron in the raw material, our MJet has the possibility to eliminate those hard to grind particles just during the grinding process. So by this way, the quality of your product will also be further improved. We have mentioned that one advantage of our MJet is it can produce powder with narrower particle size distributions than the other jet mills. Here we show you some data from our MJet and also a fluidized jet mill. So if we use the D90 value divided by the D10 value to represent the distribution of the final particle size of the material, the result we saw here is when producing the final product with the same D15 value, the D90 to D10 value from our MJet is always smaller than that value from the fluidized jet mill. That confirms the fact that the MJet can produce a powder with narrower particle size distribution. Now let's have a look about the status of generating superfine particles. Actually, we don't want to have much of those superfine particles within our final products that will influence the magnetic property of our final product. From data here, you can realize that when reaching the same D15 value, the D10 value, which represents the superfine particles of the product from our MJet, is always bigger than what we got from a fluidized jet mill. So this confirms the fact that the MJet can actually produce less superfine particles when reaching the same D50 value as the fluidized jet mill. Just now, we also mentioned that there will be variations of particle size distribution during the starting and stopping phase of the fluidized jet mill. The red curve you see here is a typical curve represents the changes of particle size inside a fluidized jet mill. So when the mill is just started from time 0, the mill chamber is empty. In this moment, you will get particles with the biggest sizes. So with the increasing of material inside the grinding chamber, the final particle size will become smaller and smaller until reaching a constant value when the material amount also reaches the best level inside the grinding chamber. If you look into the green cover, which represents the situation from our MJet, you realize that just from the beginning to the end, the particle size from the MJet is always relative constant. That means there's not really variation of particle size during the production of our MJet, and you can use the product just from the beginning of our MJet as your final qualified product. So today, the solutions with our MJet can be started from the R&D systems in the laboratory and also to the industry production systems. So no matter you want to produce a few hundred grams of product or a few hundred kilos of product per hour, we always have the right solution for you here. Okay, so that's all for the moment. Thank you again for your attention. I also want to take this chance to wish all people at IPB site in China have a nice time. And also thank you to the POWTECH team and IPB team for organizing these great events. Now I'm ready to take your questions.